This conference will now be recorded.
Hello everyone. Last class, preparation of alcohols. This topic we have already started, and hydration method for preparation of alcohols. Under that heading, two types of reactions already discussed. And now we are starting hydration by oxidation and hydrobolation. So this is the number 3. So in today's class, there will be discussion related to preparation of alcohols, that is different preparation methods for different types of alcohols, and after finishing that, the physical properties of alcohol. So these are the topics of today's class. Hydration by hydroboration oxidation. So as you can see here, two methods are indicated, hydroboration and then oxidation. So first step is basically hydroboration and the second step is oxidation. Here what happens? So here we have taken this alkene in presence of BH3 and tetrahydrofuran, which is ether, and it is used as solvent. So this is the first step, which is hydroboration, and the second step is oxidation of the molecule which is formed. So in the first step, what happens here, BH3 is added to CC double bond, and here as you can see H and BH2. So these two are the fragments that are coming from BH3. So it is added in this way, and finally the second step, as we have mentioned, it is oxidation. So H2O2 in presence of alkaline medium. Finally, BH2 is converted to OH. So it is net addition of H and OH. So that is why you can call the overall reaction as if it is hydration. Alkene when treated with diborane, diborane means B2H6. Because BH3, though we have written it here as BH3, but it cannot exist as monomer. It exists as its dimer form, which is B2H6, and it is known as diborane. So this is the reagent which is used for this method, and first it gives alkyl boranes. So alkyl borane, in general, the form is written as R3B. Now if you are thinking what is R3B, it is that will be shown after some time. So this R3B, which is known as alkyl borane, this is also actually one kind of R3B, but it is not exactly R3B, it is RBH2. So when we are saying that it is RBH2, that means you have to consider this whole part as R. So with R, BH2 is added. Similarly, if two more hydrogens of this BH2 is replaced with two more R group, then gradually it will be converted to R3B. Because per BH3 molecule, there are total 3 replaceable hydrogen. All these 3 hydrogens can be replaced by R group, and this R group is generated from the alkene that we are using as starting material. So this R3B, which is formed at first, it is known as alkyl borane. This is now undergoing oxidation. Medium is alkaline, and the reagent that we are using for oxidation is H2O2, and finally we are getting alcohol. So overall reaction is hydration of alkene. Individually, if you see, it is first hydroboration and then oxidation, but overall reaction is hydration. Now one point is very important to understand. In the previous methods, that is in last class, the hydration methods that we have seen, there we have seen Markovnikov addition. And what is Markovnikov rule, that is also detailed discussion already done. But in this hydration, one important feature of this reaction is that you are getting anti-Markovnikov product. So anti-Markovnikov rule, that is just the reverse rule of Markovnikov. In Markovnikov, we have seen that the negative part of the reagent, that is added to that carbon which is containing lesser number of hydrogen. But in this case, if you see this alkene, which is obviously not symmetrical, so these are the number 1 carbon and 2 carbon. Now number 2 carbon is containing higher number of hydrogen, number 1 carbon is containing lesser number of hydrogen. If it is following Markovnikov rule, then HO minus should be added to carbon number 1. But if you can see in the end product, it is actually added to carbon number 2. So that is why it is anti-Markovnikov addition. And this is very important feature of this molecule. Now this is also important from the point of view of, if you want to make this type of alcohol where you actually want it deliberately that anti-Markovnikov should be the product. So in that case, obviously, you have to use this reaction, not the other methods. Now we will see how this R3B is formed. First, we have taken propene as alkene, CH3CH double bond CH2. Then we are using diborane. So here how the molecule is written, it is written as if it is BH3 whole 2. That means it is dimer, so it is actually B2H6. Now BH3 is written in this way, H and BH2 two fragment, because there will be addition of H and BH2. And remember, here H is addition of H and BH2, that is also that is BH2 will be added to that carbon where your OH will be present, because actually BH2 group is converted to OH. So remember, this is also, that is the addition, the position of BH2 and OH, these two will be same. Now this molecule is actually RBH2, but remember there are two more hydrogen that you can replace. So as if now you have taken another alkene molecule and you are treating it with RBH2. So now another H will also be replaced, and RBH2 you can write it as if it is RBH and H. So now instead of addition of H and BH2 that you have seen in the first step, now as if it is addition of H and RBH, and we are getting R2BH. So this is R2BH, but still one more hydrogen. So you can write this reagent as if it is R2B and H. So now R2B and H, these two fragments will be added to these two carbon. Here H will be added in the middle carbon and R2B will be added here. So finally you are getting this molecule, which is basically R3B as it is mentioned here. And next there is oxidation, alkaline medium, H2O2 molecule and water. So finally all these that is R group, R3B, you are using H2O2 alkaline condition. So all these three R group, they will lead to the formation of 3 alcohols, because total 3 alcohols can be generated. And the fate of boron is it will be converted to BOH whole 3. Now if you put the actual R group, which is basically in this case CH3, CH2, CH2, 3 carbon. So basically you are getting finally 3 molecules of propanol. Okay, so this is hydration method by hydroboration oxidation, where the overall reaction is basically hydration. And remember, one important feature is it is anti-Marconic of addition of water to alkene. Next method for preparation of alcohol is reduction of carbonyl compound. So in carbonyl compound there will be presence of C double bond O. So if you are reducing this group, basically it is addition of 2 H. One H is added to O, another H is added to C. So now it is converted to alcohol. So this is alcohol. There may be any groups both sides. For simplicity, I have not written that. Now when it is reduction of compounds, first point we will see if you are reducing aldehyde and ketones. So starting material is aldehyde and ketones. Now when we are saying carbonyl, there may be different types of carbonyl, because ester molecule also there is carbonyl, carboxylic acid there is also carbonyl. It is a general term. So first we will see if you are reducing aldehyde or ketone by some reducing agent, obviously, then how we are getting alcohol. Aldehydes and ketones are reduced to the corresponding alcohol by addition of H2 in presence of catalyst. So this method is known as catalytic hydrogenation, because you are adding H. Now mostly the metals that are used, it is used in finely divided form, because when the particle size is very small, that is powder type of form, surface area increases, and as this reaction is going on the surface, so obviously if surface area is high, reaction rate will also be high. So that is why finely divided metals such as platinum, palladium, nickel, all these are used. So this is one reducing agent that you can use, but there are another two important reagents. That is, alcohol can also be prepared by treating aldehyde and ketones with sodium borohydride NaBH4 or lithium aluminium hydride LiAlH4. So all these, that is, these two molecules, they are actually source of hydride ion. So that is why the name is ending with hydride. And what is hydride? H carrying negative charge. When H carries positive charge, we call it proton. When it is carrying negative charge, it is hydride. If it is aldehyde, you will be getting 1 degree alcohol, primary alcohol, and if it is ketone, it will be 2 degree. So see, generally we have taken this molecule as ketone RCOR in presence of H2 and nickel or platinum. So this is one reducing agent that you can use, or you can use lithium aluminium hydride or sodium borohydride. In both cases, you are getting alcohol. So this is a general example, but if you are taking propanol, which is basically acetone molecule, we are getting this type of alcohol. If I write the structure of this molecule, it will be like this. So as we have started with ketone, we are getting secondary alcohol. If we compare the strength of, that is the reducing capacity of sodium borohydride and lithium aluminium hydride, which one is stronger? Then the answer is lithium aluminium hydride is stronger. Here we have different types of molecules. This is aldehyde, then ketone, this is ester, and this is carboxylate ion. As they were moving from left hand side to right hand side, see, ease of reduction is increasing. That means it is very easy to reduce aldehyde rather than ketone. So as we were moving from aldehyde to ketone, reduction becomes difficult. Then when you are moving from ketone to ester, it is becoming more difficult. So that is the reason here it is written ease of reduction is increasing as you are moving from left hand side to right hand side. Now the first two molecules, as they can be easily reduced, so here you can use either sodium borohydride or lithium aluminium hydride, both will work. But for these two, sodium borohydride, now it cannot show its reducing capacity. Now you have to use only lithium aluminium hydride. Fine. So lithium aluminium hydride, it is more strong, and also it can reduce all different types of carbonyl compounds to corresponding alcohol, but that is not possible by sodium borohydride. Second method, if starting material is carboxylic acid or ester, now they can be reduced to primary alcohols in excellent yield if you are using lithium aluminium hydride, which is stronger compared to NaBH4. So see, here we have taken this molecule. In the same molecule, you have aldehyde group, you also have ester group. Now as sodium borohydride, it cannot react with ester and it can reduce it. So see, it is still intact. Only this part is reduced. But when it is lithium aluminium hydride, both parts are reduced. See, from this part what you are getting? You are getting CH2H. That means you are getting 1 degree alcohol. And from aldehyde part, you are getting, this is also 1 degree. But difference is that when it is sodium borohydride, it is selective. It is more selective because it is not so strong as lithium aluminium hydride. Now, depending on your requirement, if you want in this particular molecule, if you want only the aldehyde group to be reduced, obviously you have to use sodium borohydride. But if you want both of them to be reduced to alcohol, then you have to use the more strong in LiAlH4, lithium aluminium hydride. Number 5th point, starting from Grignard reagent. So now we will use Grignard reagent towards aldehyde or ketones. So starting material, there will be two reaction partner. One is Grignard reagent, another one is aldehyde or ketone. And we'll have to do this reaction in dry ether because whenever it is Grignard reagent, always dry solvent is used. Otherwise, if there is any amount of moisture or water, then Grignard reagent that is very sensitive to water, so it will be decomposed. So that is why dry solvent is very important. And followed by acid hydrolysis. So once the initial nucleophilic attack of Grignard reagent to aldehyde and ketone, this part is done. After that, finally you have to do acid hydrolysis and then you can use water. But first step, it is in dry solvent. Second step, acid hydrolysis. If it is, okay, I'm going to the 2 points before that. Here you can see, this is a general nucleophilic addition of Grignard reagent to aldehyde or ketone. So this is the general carbonyl compound. It may be aldehyde or it may be ketone. Now as it is Grignard reagent, that means R group means there is some carbon. So carbon Mg bond, that means it is basically carbon metal. And carbon is more electronegative. So that is why negative charge will be towards carbon if you consider the polarity of this bond, and positive charge will be on magnesium. Now this negative charge over carbon, as if it is a nucleophile, so it will act as nucleophile. So as if here R minus is acting as nucleophile and double bond between carbon and oxygen will be broken. There will be negative charge over oxygen. Now, as I have said that positive side is towards Mg. That means you can write this molecule RMgx as if it is R minus and Mgx. That means the positive part. Now that will be attached to oxygen because negative charge is present over oxygen. So now you are getting this type of molecule where oxygen Mgx bond is there. And in the second step, now you have to do acid hydrolysis and OMgx will be converted to OH. So this is the reason why acid hydrolysis is done. Otherwise, it will remain in this form. So this is a general mechanism. Now, if you have taken the starting material, if you have taken formaldehyde, you will be getting primary alcohol. But if it is rather than formaldehyde, if you have taken some other type of aldehyde, because formaldehyde is the first member of aldehyde, it's the simplest aldehyde that is possible. So only this one will give you primary. But if it is other aldehydes, now you will get secondary alcohols. So here we have formaldehyde. So in formaldehyde, both sides there is hydrogen, and when R is attached, obviously now carbon, there is 2 hydrogen and 1 R. That means the carbon with which oxygen is attached, that carbon is attached to only 1 carbon. So that is it is 1 degree alcohol. But if you have taken some other formaldehyde, that is 1H is now it will be R group. So already there is 1 CC bond present, other aldehyde, and this R minus is attacking as nucleophile. So now another carbon-carbon bond is formed. One carbon-carbon bond is already there. Another carbon-carbon bond is also formed. And after this OMgx is converted to OH. Now the carbon, this carbon, it is attached to 2R group. So that means it is secondary alcohol, right? And if it is ketone, 2R group already there, that means 2 CC bonds already there, and a new CC bond is formed. This R is coming from Grignard, and finally it is now MgX is OH. So this is 3 degree alcohol. So depending on the requirement, whether we want 1 degree, 2 degree, or 3 degree alcohol, accordingly we have to take the reaction part. It may be formaldehyde for 1 degree, for other aldehydes it is secondary, and for any ketones it will always be 3 degree. One problem we will see which is related to this Grignard reagent. To synthesize 1 mole of 2-methyl propan 2-ol starting from ethyl ethanoate, how many equivalents? Because there is a gap. This is integer type of problem. It will be 1, 2, 3, whatever. How many equivalents of Grignard reagent? So this is the Grignard reagent CH2MgBr. Here R group is methyl. Will be required. So obviously these two names that are given, you have to write the structure first. That is the first thing you have to do. 2-methyl propan 2-ol. Propan means 3 carbon. 2 means if it is 1, 2, 3. Middle carbon there is OH. but it is also 2-methyl. That means one methyl group will also be there. Now, to satisfy the valency, it will be CH3. This is also CH. So this is basically Me3COH. So you want to make this because it is mentioned to synthesize 1 mole of this molecule. Now from ethyl ethanol. Now what is ethyl ethanol? From the name you can understand. This is obviously some ester molecule, right? Ethyl ethanoate. Now when it is ester, in general if I write it in this way, 2 R groups. Now this R prime that is written first. That means here ethyl is R prime and ethanoate. Ethanoate means this is also 2 carbon. So this part should be 2 carbon and R prime that is also 2 carbon. So what should be the structure? It should be CH3CO O CH2 CH3. Now when it is ester and you are using Grignard, here the mechanism that you have seen in the previous slide, that is related to aldehyde and ketone only. There is no such OR prime group attached to carbonate, but now you have OR prime group, right? Now when it is treated with some Grignard reagent R minus, when it attacks, normally what we have seen, that negative charge over oxygen, but here what happens, this CO bond is broken. So first you will be getting CH3COR. So this R group is coming from Grignard reagent, but now from ester what you have obtained, you have obtained some ketone molecule. So further addition is also possible. So another RNGBr can also attack, and now this CO double bond will be broken. So finally what you are seeing with this carbon, that is a carbonyl carbon, now it is attached to one CH3 and 2 R groups, and it is converted to alcohol. So further addition is not possible. So how many Grignard reagent we are actually using? The first Grignard reagent we have used, and this is the second. So basically it is now total 2. So see, this is the mechanism. This is ethyl ethanoate. Fine. This is 2 carbon. This side also 2 carbon. So CH3MgBr is attacking. This bond will be broken. So as it is CH3, so this part, the right hand side part is coming from Grignard reagent, and this CH3 it was already there, and OCH2CH3 that is removed in this form, which is ethanol. This is number 1 Grignard reagent. This is the second Grignard reagent. So per mole of the ester molecule, we are using 2 moles of Grignard reagent, right? So now it is OMGBr, and after acid hydrolysis, we will be getting this molecule. So see, this is actually Me3COH. So answer will be 2 equivalent. 2 equivalent of CH3MgBr, not CH3MgBr, any Grignard reagent, whatever you use, it will always be 2. So for ester, per mole of the starting material, that is the carbonyl compound, we are using 2 moles of Grignard. But if it is normal aldehyde or ketone, obviously it is 1:1 reaction. Fine. Now after preparation methods of that is the general methods for preparation of alcohols, now the topic is manufacture of methanol and ethanol. Now when we are saying manufacture, that means it is large scale production, and specifically we have mentioned these 2 alcohols. It is not general, there are specifically mention of 2 molecules of alcohol. Now these 2 because of their application, they required in huge amount, so that is why large scale production is required. So first we will see manufacture of methanol, which is the simplest alcohol possible, CH2OH. So what we do at first, water gas. What is water gas? It is mixture of carbon monoxide and hydrogen. It is prepared from coal, which is carbon, 1270 Kelvin, very high temperature. So what is done here? Carbon is treated with water. It is converted to water gas. Now this water gas, it is treated with zinc oxide and chromium oxide catalyst. And finally, we are getting CH3OH. Ethanol manufactured by fermentation method. It is only applicable for ethanol. What we take glucose molecule. It splits into two pyruvate molecules before fermentation. And the energy that we are getting from this exothermic process. What is the exothermic process? When glucose is splitting into pyruvate molecules. This energy which is liberated because it is exothermic reaction, that is used to link inorganic phosphate to ADP, which is adenosine diphosphate. This is a full form of ADP. So see here, glucose molecule, it is splitted to 2 pyruvate, and in this process the energy that is liberated, that is used for conversion of ADP to ATP, adenosine diphosphate to triphosphate. That means one more phosphate is now attached. Okay, now the pyruvates, next it is broken down into two acetaldehyde molecule. This is acetaldehyde, which emit two carbon dioxide molecules as waste product. So this is decarboxylation, this is waste product. The acetaldehyde is then converted into ethanol. Finally, we are getting ethanol utilizing the energy and H provided by NADH. So full form that is related to biology basically. Just remember here the reducing agent required because you are converting aldehyde to ethanol. So this reducing agent is basically NADH. NADH is supplying this H, and as a result now there is addition of H and H, that is 2 H atoms are required. So now in this process, as it is mentioned, utilizing this energy, that means the energy that we are getting here, that is also utilized here. Fine. So this is the fermentation method where first you have taken glucose, formation of pyruvate, then pyruvate is converted to acetaldehyde, and finally acetaldehyde is reduced to ethanol in presence of NADH, and the fate of NADH, now it is converted to NAD+. So these are the different steps involved in fermentation method. So here what type of enzymes are actually used, that is mentioned when it is conversion of pyruvate to acetaldehyde by the removal of carbon dioxide. Basically pyruvate decarboxylase enzyme is used. Now so enzyme name you will get there is easily you can understand that what is the role of this enzyme, because when it is mentioned pyruvate decarboxylase, this name is basically generated from decarboxylation, because decarboxylation means removal of carbon dioxide. Now this enzyme is helping this process, that means the name, that is why the name of this enzyme is decarboxylase. And pyruvate decarboxylase, it is not that it can decarboxylate any molecule, it is specific for pyruvate molecule. So that is why the name of this enzyme is pyruvate decarboxylase. So these are the natural catalysts that is present in living things. Okay, so that is, it is biology, it is also called biological catalyst. Their role is very specific. It can decarboxylate only pyruvate, and when it is conversion of acetaldehyde to ethanol, now alcohol dehydrogenase is used. So here also addition of hydrogen is occurring to C and O. So that is why here the name is like this, alcohol dehydrogenase. Now the name is as if it seems that dehydrogenation means what? Removal of H. Hydrogenation is addition of H. Now see, it is mentioned clearly alcohol dehydrogenase. That means alcohol will be dehydrogenated to acetaldehyde. So if you consider from the point of view of alcohol, it is alcohol dehydrogenase. But if you consider the opposite process, which is aldehyde to ethanol, now it is obviously hydrogenation. So that is why as it is dehydrogenation with respect to alcohol, that is when if you consider the reverse reaction, that is why the name is like this. Fine. So remember, in ethanol manufacturing from by fermentation, starting from glucose, there is involvement of pyruvate in the first step, then there is formation of acetaldehyde, and finally it is the desert molecule, which is ethanol. Next is preparation method of glycol. Now this molecule is very specific because here we have more than one OH. So that is why its preparation method we are discussing separately, not in the general method of alcohol. Because here you have two OH group, so that is why obviously its preparation method will not be same as you have seen in case of other alcohols, where only one H is present. So first we'll see what is glycol. It is any type of organic compound that belongs to the alcohol family, obviously, but with two hydroxyl group attached to different carbon, not in same carbon. If it is same carbon, properties will be completely different. But it is two adjacent carbon, not always it is necessary, but not in same carbon. Now, glycol, it is the general term for this type of molecule. But as the simplest molecule is this one, that is CH2H, CH2H. So that is why this name is also used for the first member of this type of molecule. So you can call it ethylene glycol or simply glycol. It is the simplest member of this class. You can also call it 1,2-ethane diol, and that is according to IUPAC. Because in IUPAC, what we do, we find the longest chain. So this is the longest chain, and this is one carbon, this is two carbon, and it is ethane derivative, right? Ethane is CH3, that is C2H6. Now two hydrogens, two carbon hydrogen bonds are now replaced by two carbon OH bonds. So that is why the name 1,2-ethane diol. It is a prominent member of the class of dry hydroxy alcohols known as ethylene glycol, dihydric alcohol, or diols. How you can make it? First method is, there is not just one method, several methods are there. First method is starting material, what we have taken, ethylene oxide. Now ethylene oxide, as it is not very stable, normally you have to make it starting from ethylene in presence of oxidizing agent O2 and Ag2O. Here it is catalyst. Ethylene oxide is obtained after catalytic oxidation of ethylene. So this is the method by which you can make ethylene oxide. So this is our actual starting material. So if what we are doing, we are adding dilute acid. That means water is there, H plus is also there. You can also use base. So finally, what we are getting? We are getting ethylene glycol. So this, as it is symmetric molecule, you can consider the cleavage of any of these carbon-oxygen bond, and another oxygen, one oxygen is already there, another oxygen will come from water. So as if the mechanism, first there is protonation of this molecule, and finally if another water molecule is attacking any site, so this carbon oxygen bond will be broken and there will be two OH group. So this is the first method. Second method, from oxidation of ethylene. Now directly you can oxidize this ethylene molecule by cold alkaline KMnO4. Remember this reaction we use for determination, identification of whether any CC double bond, that is unsaturation, is present or not, because alkaline KMnO4, not alkaline, that is KMnO4, it's aqueous solution, it has specific purple color, it is very intense color, but when it is reacting with any molecule having unsaturation, after this reaction, this color of purple color of KMnO4 is discharged, and that is the indication that unsaturation is present. So same reaction you can also apply for ethene, so that you can prepare this glycol molecule. This alkaline permanganate solution is also known as Bayer's reagent. You should also remember this name, because if in question, instead of that is the mention of permanganate, if it is mentioned that in presence of Bayer's reagent, then so that you can understand, so please remember this term also. hydroxylation. It is basically dihydroxylation because two OH groups are added to CC double bond. Third method. Again, we have taken ethylene, but another reagent is HOCl. Fine. So HOCl, you can consider as if it is HO and Cl. So these two fragment, now it is added to C and two individual carbon. So first we are getting this type of molecule, but finally when it is treated with aqueous sodium bicarbonate, Cl is now replaced by OH. Fine. And these are the byproducts. So in this way also we can make glycol. Number 4, from ethylene dibromide. So this is ethylene dibromide molecule, CH2Br, CH2Br, and it is treated with sodium carbonate and water, and finally it is aqueous sodium carbonate. Finally both this Br and Br, they are replaced, that is substituted by OH. These are the byproducts. Fifth method, starting from ethylene chlorohydrin. So ethylene chlorohydrin is basically this molecule that you have already seen in method number 3. So same molecule is written here, but two molecules are taken, and in presence of milk of lime, which is nothing but calcium hydroxide. Now what will happen? This CCl bond, now it is replaced by OH, and as calcium is that is C, two molecules we have taken, ethylene chlorohydrin 2, and this is 1. That means per calcium hydroxide, two molecules can take part. So here 2 OH is present per CaOH also. So obviously 1 calcium hydroxide is enough. So 2 Cl, they are replaced by 2 OH, and the fate of Ca is now it is converted to calcium fluoride. So this chlorine is coming from CH2Cl. So these are the methods by which we can prepare glycol. So all these reactions, you can see one thing is common, that is starting material is ethylene. Here it is not written directly, but this CH2Br that you are seeing, ethylene dibromide, that is also prepared from ethylene by addition of bromine. So we can say in all cases ethylene is the common starting material. After glycol, next is glycerol. So this molecule, as you can see the picture, this is known as glycerol, and here we have total, this is trihydroxy. 3 OH groups are there. Now glycerol is very important because they are naturally present as fats, and it is also found in long chain fatty acid in the form of glyceryl ester. So they are not directly present in fatty acid. Fatty acid is long chain molecule where ester linkage is there. And as we know, how we prepare ester, starting from acid and alcohol, right? So as we are saying, it is fatty acid. So if you have taken one fatty acid and this type of glycerol, so these are the basically they will be acting as alcohol. So per glycerol molecule, 3 acid molecules can react because there are a total 3 OH group, right? So that is which is known as triglyceride. The alkaline hydrolysis of these fats gives glycerol, and the reaction is known as saponification. So as we are discussing preparation of glycerol, so here starting material that we have taken, triglyceride. See, here ester linkage is present. Ester linkage, this is also ester linkage, this is also ester linkage. Groups may be different, may not be different. Here all the 3 groups are different, R, R prime, R double prime. And as you have to break total 3 ester, so that is why 3 NaOH molecules written. Fine. And after breaking off all these bonds, you are getting glycerine, which is nothing but glycerol. This is another name. And from the right hand side part, now we are getting total 3 sodium salt of carboxylic acid. So if you simply acidify it, the sodium salt, it will be converted to OH. ONA, that will be converted to OH. but you are getting 3 different acid molecules, and if all these R groups they are same, then obviously you will get 3 molecules of the acid. This is a general expression. If you have taken this type of triglyceride where R group is basically same, see, as we have said, it is long chain fatty acid. So here you can see CH2 whole 14 times CH2 and then CH3. So this is simply very long chain alkyl chain. So all these are same group. So finally what we are getting? See, we are getting NaOCO R, and total 3 molecules will be there. And this particular molecule where you have this type of chain CH3, then 14 CH2, then CO2 minus or CO2H, whatever, it is known as sodium permeate. But if it is not sodium salt, if you are when it is in metal salt form, it is actually soap molecule. But if you are acidifying it, then it will be OH, then the name will be palmitic acid. But as it is in salt form, we are calling it as sodium permeate. Okay, so this is the method, that is a saponification of triglyceride by which you can prepare glycerol. After finishing preparation methods of different types of alcohols, next our topic is physical properties of alcohols. Now as we know from, if we write the general formula of alcohol, ROH, there are basically 2 parts. So this is the alkyl group and this is the hydroxyl group. Now the properties of alcohols, it is mainly because of this hydroxyl group, because whenever you have any alkane and you are replacing one H with OH, drastically the properties will be changed, because now you have OH rather than H. The nature of alkyl group simply modify these properties. So we are trying to say that mainly the properties of alcohols, it will be basically because of this OH group. But that doesn't mean that R group has no role. That is not true. It will also modify its properties in a simple way, but there are some effects of R. So main role is for OH, but R group can also play some role, because R groups, it may be a very long chain, it may be short chain, it may be it may contain some branching or may not contain. So depending on all these factors, it can simply modify these properties. It is observed that lower alcohols, that is methanol, ethanol, propanol, they are mostly colorless liquid when you are considering at room temperature. Okay. Now when you are moving towards higher number, that is up to propanol, it is 3 carbon, CH3, CH2, CH2H. But now when you are moving to 4 carbon, 5 carbon, in this way up to 12 carbon. Now the nature of these molecules at room temperature is they are becoming viscous. That means they are becoming more dense. So these are colorless liquid. If you see from far, it is simply just like water. But when you are increasing the carbon number, it is becoming viscous, more dense, oily in nature. And if you have 13 or 14 carbon, that is greater than 12, now they will be waxy type of solid. Okay, so as the molecular weight is increasing, because carbon number increasing means hydrogen will also increase, molar mass will increase. So gradually the physical state is becoming from liquid, then to some viscous liquid, and finally waxy solid. But they are colorless in nature. What type of smell we have? There is a sweet smell except for glycerol and few lower alcohols. They are flammable, we all know that, and they produce a blue flame. Here we will see the first property, which is after finishing this physical state, acidity of alcohols. Now as in alcohol there is OH group, and in OH you also have this proton. So this proton is basically responsible for its weakly acidic nature. Not very strong, they are very weakly acidic. Alcohols, because of this H, presence of this H, they can react with active metals, mainly alkali metals, and they can form alkoxide. So alkoxide is when you are converting ROH to ROM. M may be Na, M may be potassium. So this is alkoxide because now it is RO minus M plus. So RO minus is in general called alkoxide. If it is methyl O minus, it is methoxide. If it is ethyl O minus, it is ethoxide. But general term is alkoxide. So this H is replaced by metal because it has some acidic character. So that is why we can get alkoxide. Primary alcohols are generally more acidic in nature than secondary, and tertiary alcohols, that is first, that is if you compare acidity of primary, secondary and tertiary, keeping other factors same, that is same number of carbon, hydrogen if you keep maintain, then it is observed that primary alcohols, they will be more acidic, because when branching is increased, then the plus I effect, that is electron donating effect, that will also increase, and as a result the H, its acidity will decrease, because when electron donating effect is not very high, H will be more electron deficient and in acidity will also increase. So that is the reason primary alcohols are generally more acidic than secondary and tertiary, as EDG, electron donating groups attached to hydroxyl groups, increases the electron density, and as a result acidity decreases. As you can see in this pH scale. Now what is pH scale? pH means negative logarithm of H plus. So when H plus concentration is very high, what we say? Acidity high. But if you take log H plus and if there is a negative sign and then it is pH. So what it means, when H plus concentration increasing, pH will decrease. So it is inversely related. That means when pH is very low, acidity is very high. And what about pK? pK is just like negative logarithm of HK. pK is negative logarithm of K. So K is dissociation constant of acid. If I write in general ROH, dissociation is RO minus NH plus. So this type of dissociation, the corresponding dissociation constant, that is K. That means when Ka value is very high, this type of dissociation of ROH to RO minus and H plus is very high. That means when Ka is high, acidity is also high. But remember, when acidity high, pK is less, because it is inverse relationship. There is a negative sign, right? Now here this pK scale, as you can see, as we are moving from left to right, pK is gradually increasing. That means when you are moving from CF3CH2OH to methanol to ethanol, then isopropanol, and finally tertiary butane, pK is decreasing. It is actually not pH, it is pK. Now pK decreasing means what? This is maximum acidic and this is minimum acidic, which is clear from this pK. And see here, this red line that you are seeing, this particular value is for water. So all the molecules that are in the right hand side of this red vertical line, which is for water, that is these three molecules, their pK is even greater than water. So it means what? Acidity of water, that will be in between these two. If you move towards methanol and CF3CH2H, these two are more acidic compared to water, but these three less acidic compared to water. Right? So this line is for methanol, this one is for CF3CH2H. There is also mention of phenol, but that is completely different topic. We'll discuss it separately. This is actually having maximum acidity, and why it is so, that will be discussed separately. But in these examples, this is maximum acidic, and the reason is here you have 3 fluorine. So fluorine, as it is very electronegative atom, it will increase the acidity of this H. So this is the scale of pKa. From this we can understand how acidity is decreasing or increasing, and you can also compare with water. So as we have mentioned, they are very weakly acidic in nature, and that you can easily understand here, because water, it is even lesser acidic than water. That means they are highly uh, mild acid, right? After acidity, next is solubility of alcohol. Hydroxyl group in alcohol, they are involved in the formation of intermolecular hydrogen bonding. That is hydrogen bonding between two different molecules. So in this picture, we have this green color, that is ROH, and in between there is also water molecules. That means they can be soluble in water because they can form this type of hydrogen bond. So the oxygen atom of water, it is taking part in hydrogen bonding with H of one alcohol molecule. Then this H of water, it is making hydrogen bond with oxygen of another alcohol. So in this way, the chain can be extended both left hand side and right hand side. And because of this interaction, they are soluble in water. However, the alkyl group that is attached to the hydroxyl group, they are hydrophobic in nature because they are basically carbon and hydrogen, hydrocarbon part. So obviously they will be hydrophobic. So that is the reason when there is increase in the size of alkyl group, that means hydrophobic part is increasing. So solubility of alcohol will decrease. Okay. Alcohols with more than two H groups are more water soluble than similar alcohols with only one. So if you are comparing ROH type of molecule and suppose there is ethylene glycol, so obviously ethylene glycol, that will be more soluble because OH, with increase in OH group, hydrogen bonding will increase, solubility will also increase. So now focus on this point. Solubility of alcohol decreases with increase in size of alkyl group. So see, methanol, ethanol, propanol, their solubility in water is very, very high. It is simply mentioned infinitely soluble. And here the values that you are seeing for other alcohols, butanol, pentanol, gradually the carbon number is increasing. Here we have 1 carbon, 2 carbon, 3, 4, 5, 6, 7 in this way, right? Now, as it is mentioned 9, it means it is the solubility of butanol is 9 gram when it is 100 gram of water. So in bracket it is mentioned gram per 100 gram of water. So see how it is decreasing, and when you are moving from propanol to butanol, there is a huge shift. Just you are increasing 1 carbon from 3 to 4. From infinitely solubility, now it is drastically decreased to 9. And as you further increase carbon number, it is alkyl chain decreasing, hydrophobic nature in the molecule increasing. So it is becoming less and less. And the last one, see, 10 carbon, it is now insoluble. Here we have this graph which is based on these values, more or less, not exactly. Here in the y-axis we have taken solubility of water at room temperature, gram per 100 ml water. Now as water, its density is almost 1, near 1. So 100 ml and 100 gram, this will more or less same. That is 100 ml, it is approximately equal to 100 gram. So this is y-axis, all these values, 2, 4, that means 4 gram per 100 ml. Then there is this type of sign. It means there is a huge shift in scale, because when carbon number, which is in the x-axis, suppose you are having methanol, then ethanol, then propanol, and then butanol. Now see, these three almost having same value of solubility, and their values are actually very high. But if this type of scale jump we do not do, what will happen? In the same graph you cannot show them. So there is sign, the sign, same sign is here also. That means here some scales we have jumped, right? So these values actually very, very high. if we do not jump, it is not possible to present in the same graph. That is why this type of jump is done. So when you are moving from 3 to 4, now there is drastic decrease in the solubility. Then 4, then 5 carbon, which is around near around 3, and when it is 6 carbon, it is around 1, like this. Fine. Though it is not exactly matching, but it is qualitatively same. So in this way, from this graph, you can understand as the carbon number is increasing, that means the hydrophobic part is increasing. Obviously, the solubility of alcohol, that will decrease. That is solubility in water, that will decrease. Boiling point. Boiling point, here in the graph, same type of graph we have taken. Number of carbon atoms in the x-axis. All these observations you are seeing, that is at room temperature. Boiling point in degrees centigrade, there is scale jump again. Fine. So 40, 80, all this means 80 degrees centigrade or 160 degrees centigrade, like this. So when it is 1 carbon, it is around in between 40 and 80. And as you are increasing the number of carbon atoms, boiling point is also increasing. There is smooth increase, right? The boiling point increases with increase in the number of carbon atoms. That means when carbon atoms increasing, hydrophobic part is increasing. There is increase in van der Waals forces. Now hydrophobic part, that is the alkyl part, ROH. Now how it is related to van der Waals force? Suppose R, as it is carbon and hydrogen, there is no such polarity, right? But suppose at a particular moment in this region, if I write it in this way, there is accumulation of negative charge on one side, positive charge on other side, and another R group, if it is oriented in this way, there will be some interaction between these oppositely charged. So this is actually van der Waals force, though there is no direct any polar group, but at a particular moment, if there is accumulation of negative charge on one side and accumulation of positive charge on other side of this molecule, that is not molecule in this hydrophobic part, there may be van der Waals interaction present. So as these R group are increasing, there is increase in van der Waals forces, and to overcome these van der Waals forces, you have to put more energy, and that is the reason boiling point is increasing. Decreases with increase of branching in carbon chain. Now, if you keep carbon number same, and if you are increasing the branching, suppose you have butanol, 4 carbon, then OH. But same molecule, if you have tertiary butanol, now it is more spherical in nature, this is linear. Now when it is more spherical in nature, that is increase of branching. More spherical means we know sphere shape, it is always having less area, surface area. That means decrease in surface area, but van der Waals interaction is directly related to surface area. So when there is decrease in surface area, there is also decrease in van der Waals force, and that is the reason boiling point decreases. But remember, you have to keep carbon number same, because if you don't keep it same, this factor will also change the boiling point. So that is why keeping carbon number same, when you are increasing branching, boiling point will decrease. Okay, so this point we will finish in the next class. There are some more points to be discussed, so we will end the session here. Thank you for listening.